All right, so that quiz was really just testing some basic ideas. Because I noticed a lot of errors, I'm going to go over it right now. The first question has two functions. They're both in the correct form. In other words, x minus vt or x plus vt. If you stick it into the wave equation, they'll work. So the first one's true. The second one has a problem in that one function has an equivalent velocity of 2v and the other v. So that will not satisfy the same wave equation by putting two of them together. So this one would be false. A train is moving away from you with constant speed. So that means its frequency is less than it would be if it wasn't moving. So it puts out a whistle, constant amplitude and frequency. Both the intensity and frequency of the sound you are hearing are decreasing with time. That's not true. The intensity is decreasing with time, but the frequency is constant. It's lower than it was before if the train was not moving, but it's not changing with time. All right. A train is moving towards you, slowing down until it reaches you at the left. So it's moving towards you, so that means the frequency is higher than usual. But since it's slowing down, that frequency is going to decrease. So that's going to be true. Right? It's slowing down. It's higher than it is compared to being stationary, but then it's slowly decreasing towards you. The amplitudes of two sound waves differ by a factor of 10. That means the intensity differs by 10 squared. Intensity always goes as amplitude squared. So that's 100. Take a log of 100, that's 2. And then you multiply by 10 to get the sound level. So it should change by 20 decibels, not 10 decibels. So the last question is false. OK, so the theme of today is superposition. All right, that's built into the first couple questions of the quiz. But the basic idea is if you have two waves, each of which satisfy the wave equation, then the sum of those two waves satisfies the wave equation. In fact, you can sum as many waves as you want, and they satisfy the wave equation. OK? So the basic idea is, I'll write it down. OK. So that's the key idea. It's called superposition. That means waves will go through each other. Like if you have a wave coming this way and a wave coming this way, when they meet, they'll sum up their amplitudes, and then they'll keep going through each other. There are all kinds of effects. Now, one of the important results of this is we know that a sine and a cosine of the right form, sine kx minus omega t, that satisfies the wave equation. That means we can add up all kinds of sine waves, and that'll still satisfy the wave equation. What that means is that any wave, any form that you have can be built up from a sum of sine waves. That's a very important result. Any wave can be built up by a sum of sine waves. So any wave can be built from a sum of sine waves. Right? And each of these sine waves may have different frequencies. They will have different frequencies. So you just add them up. It's much like, you know, you have a vector in 3 space. A vector can be always written in terms of 3 vectors. Right? What are those 3 vectors? Right, exactly. I, J, K. Right? You can always write them in terms of that. So you can write any function in terms of a whole bunch of sine waves. That process, figuring out how much of each sine wave is in there, is called Fourier analysis. So this has a name, Fourier analysis. Now, so this is a topic you'll almost definitely see later on in your career, and you'll learn how to do it. Although usually we don't actually do it. We usually use a computer program to numerically figure it out. You may have seen it in some contexts where, like an audio signal, if you have a I think many of your phones will do this. You take in an audio signal and you can look at the spectrum of the signal. How much of each frequency is in there? That is a Fourier transform. That's what's called a Fourier transform, and the process is called Fourier analysis. For this reason, we will focus, the rest of this class will focus on just looking at waves that are sine waves. All right, so we're just going to look at sine wave functions. All right, so we're going to look at sine waves. And we're going to look at 3 topics. One is interference. Which is due to 2 waves, 2 sources, same frequency. And the key issue here is path lengths. That's the key. All right? So in other words, you have a sine wave, y equals, and you have 2 waves, 2 sources. Omega will be the same, t will be the same, k will be the same, but x will be different. There'll be different paths. And we want to see what the effect of that is. All right, so that's one topic. The second topic is beats. And this is when you have 2 sources, same x and t, but different frequencies. Okay, so we'll look at that. And that effect you may sometimes hear, although audio systems are better at eliminating it nowadays. But in the old days, you would hear this as a kind of low rumble in the sound. We'll show you an example of that. And the third is standing waves. All right. And here, what you have is an incident and reflected wave adding together. So they have the same time dependence, same frequency, same wavelength. Everything's the same. They just add in a certain way. Okay? And we'll talk about that at the end. Okay. So we have this. You should be able to show. We won't do this exercise right now, but I strongly urge you to do it on your own time. So let's take a look at interference. So that's the first topic. So this is an easy topic to explain, and the ideas are pretty straightforward. Let us say we have 2 sources. So this is source 1, source 2. They're in phase in every way, except the sources are at different positions relative to where you hear. So let's say you're hearing it over here. That's your ear. I don't know, not my ear, but maybe somebody's. All right? So there are two distances. That's one for x. That's the other. So that's x1 and x2. All right? So what we hear over here is a sine k x1 minus omega t plus a sine of k x2 minus omega t. All right, so that's what we hear. We just sum it up, and we hear those two. So the question is, what are we actually going to hear? Is it going to be loud or soft? Loud or soft? Okay, what is it going to be? Well, what we want is the argument of this and the argument of this. That'll tell us what's going to happen. Right? So what we have is if kx1 minus omega t equals kx2 minus omega t plus 2 pi times some integer, then the arguments are exactly the same. Everybody see that? The arguments are the same. Right? Because the argument of a sine or cosine, if you add 2 pi to it, doesn't change anything. Everybody agree with that? So when this is true, and we can rewrite this as kx1 equals kx2 plus 2 pi n, because omega t's are the same. And then we get kx1 minus x2 equals 2 pi n. And that implies, now what's k? Anybody remember what k is in terms of the wavelength? 2 pi over the wavelength. So we have a 2 pi over lambda. The 2 pi's will cancel. So we get x1 minus x2 equals n lambda. So this is the key result. All right? And this is for maxima. So in other words, when those two signs add up, we get a high sound. They add up. However, if x1 minus x2 is a half fraction of a wavelength, either 1/2 of a wavelength, 3/2, 5/2, then these two will differ by pi. And then one sine wave will be up, and the other will be down, and they cancel. Everybody see that? And you get a minimum. So if x1 minus x2 equals, one way of writing that is 2n minus 1 lambda over 2. If that is the case, then you get a minimum in the intensity. All right? 2n minus 1 is always an odd number. Right? N equals 1. 2 minus 1 is 1. N equals 2. 2 minus, you get 3. 3, you get 5. And then times a half wavelength. All right, let's see this in action. All right, let's see if this works. All right, so I have two sources, and they're putting out waves. All right, so this is what's happening. And you can actually sort of see the maxima and minima, coming out. There are these sort of lines of waves that interfere. But now I'm going to turn the sound on. Everybody hear that? Now watch what happens as I move this guy. Right now it's at a minimum. Now it's a maximum. Now minimum. Now maximum. All right, so you see you can get different sounds are heard in the room, okay? Now what are the conditions? So we have to have a single frequency. The waves have to be in phase. They have to start at the same time. So notice here there's no extra phi here compared to here. They're in phase with each other. That's very important. Usually the way you achieve that is these two speakers are hooked to the same electronics. So they're putting out the exact same thing. So if you have two speakers and they're putting out the exact same thing, you can create this effect. And you can see it if you do it at a constant frequency. So there's one frequency. If you have many frequencies, then it'll wash out. Because many frequencies means you have many different lambdas. So some of the lambdas will be minima, some will be maxima, some will be somewhere in between. So you need to have a pure sound. Notice this is a pure sound, right? It's one tone. All right? So this is an example of interference. All right, interference is not that important for sound waves. It's not used very much. All right? Even in a concert hall, you won't have it as a big effect. It's not a big effect. Where it really is very important, again, is with light waves. All right? There's so many instruments that depend on interference. All right? For example, when we look at spectral lines from the sun or something else, some material that is having excited atoms, and those atoms are giving off light, they give light off at a particular frequency. In order to get that frequency, one uses a spectrograph, which is based on interference. All right? It picks out the particular frequencies that you're looking for, and then it puts those frequencies at different locations. So you'll see a line here, a line there, a line there, a line there, corresponding to different colors. All right? And you can tell very accurately whether those lines are shifted or not due to, for instance, the Doppler effect. All right? So that is a very important use of interference. Interference is also was used in the Michelson-Morley experiment that I mentioned to you. In that case, the two paths were one path, you had a source coming like this, and then you had what's called a half-silvered mirror. Let's see if I can get that right. So one part of the source was going that way, another was going like that, and then you have another mirror comes up like that, and then another mirror here and goes like this. So you have two paths that the light is going on. All right? And by turning the Michelson-Morley experiment, in principle, you were turning the apparatus relative to this ether medium. And so the path lengths should change a little bit. And you see a bunch of fringes, literally little fringes. I've seen it on it, because I see a Michelson-Morley experiment. You see a bunch of lines. And then if those lines shift as you turn the apparatus, then you know that there's an ether. If they don't shift, which is what they found, then there is no ether. There's no Doppler effect due to the medium in the vacuum. All right? And this is very important for the idea of special relativity. All right? So interference is very important for light waves. It's also some of the key conceptual ideas in quantum mechanics are based on interference effects. So you send a bunch of light photons, all right, through two slits. So you have a source over here. It's putting out light. And you have two slits here. So the light can go through either one. And if you look over here, you will get an interference pattern. There'll be a maximum in the middle, and then it'll fall off like that, something like that. Okay? So you'll get what's called an interference pattern. If you do one photon at a time, it'll slowly build up that pattern. However, if you try to figure out which slit the photon went through, if you track which one it went through, the interference pattern disappears, totally disappears. Okay? So this is part of what called the uncertainty principle in quantum mechanics. And it has probably the most astounding conceptual revolution in all, not only physics, but all intellectual history. It's something that physicists still can't quite understand. They can't understand why it is the way it is. They know how it works, but not why. Okay? So the double slit experiment is a good example of how to measure that. And nowadays, there's some undergraduate labs that actually have built in some of these apparatus to see this. Okay, so that's interference. So the next topic I want to talk about is beats. So we're going to talk about, when I say two sources, what that means is you might have one speaker, but putting out two sounds. Right? Two frequencies at the same time. All right? That way we don't have to worry about interference effects. So we have the same x, same t, but different frequencies. So here's what we're doing. Mathematically, we're adding two sine waves, kr minus omega t, and the other has a slightly different k, and a slightly different omega. Okay, so you have omega plus delta omega, k plus delta k. And we want to see what happens when we add that together. All right? So I'm going to do it mathematically. Then I'm going to show you numerically the same thing. And then we'll talk about what it means. All right. So in order to figure out how to do this mathematically, we have to recall some trig identities. Namely, the sine of a plus b is sine a cosine b cosine a sine b. And then you have sine a minus b equals this. All right? So we add these two together. And what you notice is this term cancels with this. And so you get 2 sine A cosine B. Then I make a change of variables. I'm going to let A plus B equals C. A minus B equals D. And if you work this out, then you get sine of C plus the sine of D equals 2 sine of C plus D over 2 cosine C minus D over 2. Okay, so the key idea here is that this thing here is a product of two sinusoidal waves. One with roughly the same frequency, C plus the average frequency, and the other with the difference between the two. So I apply that to the formula above for K and omega. So what I get is, so all I'm doing is applying it to above. Here's I'm adding the two together, and here I'm subtracting the two. So you get delta k and delta omega. So I stick that in. Here it's the same. And here, delta k we'll assume is very small, and delta omega very small. So it's approximately the same as it was before. One could leave this in if one wanted. All right, so it's a little different. All right, so that's the result you get. So the key idea here is you have the original sine wave for one of them doubled up, but it's modulated by this cosine. All right, what is that going to look like? All right, so what I'm going to show you is what it looks like. So I'm going to actually show you the computer program that does this, because it's so simple. All right, so what I'm going to do is I have a little loop in my program that calculates, all right, at all different times. It takes y1 equals the sine of omega t, y2 equals sine omega t, and then y is the sum of those. And then I plot all three of them. Okay? I add a little extra here so that all the plots are separated on the graph. All right, so let's see what this actually looks like when we do the calculation. So here's the program. So I'm going to start with no difference between the frequency. All right, so I calculate it, and there you see the result. All right, so here's the first y. Here's the second y. And as you expect, there's no difference, so you just add them up. You get twice as big. All right. The frequency turns out to be, by the way, this is y versus x, or you can do y versus time. Either way, it'll be the same. So what I'm going to do now is just change the frequency by around 0.2. 0.2, and I'll calculate it again. So that's what you see. And these are called beats. Okay? So the inside frequency is very similar to this, or this. But this frequency is much lower, right? The period is longer, the frequency is smaller. And that's because this frequency here, from here to here to here, that frequency is based on the difference between the frequency of this and the frequency of that. All right, let me ask you a question. Now I'm going to change this to 0.1. What should happen to this curve? And what I mean is you have a certain distance between here and here, right? That represents the period. Is that going to get bigger when I go from 0.2 to 0.1, or smaller? Look at this. You can look at this result here. You can imagine that we're just looking at this at a particular location, or you could set this a constant, or you can look at this at a particular time, either way. So think about it. Are you going to get, is the spacing between the minima, this thing here, as I go from 0.2 for the difference in frequency to 0.1, is it going to get bigger or smaller? All right, so let's see what actually happens. So I'm going to calculate it. It got bigger. Why? Because this frequency, this period here, is the period of the difference frequency. The difference frequency got smaller, so the period gets bigger, right? f got smaller for the envelope, the period got bigger. Does everybody know what I mean by envelope? So this part of the curve is called the envelope of the curve. And this is what's inside. And that inside part is oscillating like this. Okay? How does this come about? As I said before, if you have two frequencies coming out of a speaker, and they're very close but not quite the same, they can produce a very low frequency sound. And this you hear is a kind of rumble, like a bass. It's like you added an extra instrument to your orchestra, all right, that had a very low sound, or a drum. Sometimes it sounds like a drum beating, all right, and that's why it's called beats, I guess, because you're beating on a drum, something like that, all right? Okay, so that's the idea of beats. So the last topic is standing waves. And the key idea here is, and we'll see it in practice, I'll show you a simulation. You have, let's say, a string, like a violin string, fixed at both ends, and it's set in motion. So a wave moves from one end to the other and back. So that means, and it keeps doing that because, let's say, you keep playing the violin, so you keep exciting the sound. So what you're essentially doing is you're adding two waves, one going in the one direction and the other going in the opposite direction, right? Because when it hits the end, one wave is going towards the end, and then the other is reflected from the end. And it turns out, on reflection, you get a minus sign, all right? The wave is actually, if the end is fixed, the wave is inverted from what it was before. And one can see that by looking at what happens to the tension in the wave right at the end. Okay, so if the wave is coming in at the end, so let's say the wave is looking like this, and you're right here at the end, okay, there's a tension on this wall going this way, right? So the tension on wall, just like any string, the string will pull on it, right? So that means the wall will pull down on the string. And because it pulls it down, it will invert the wave, right? It will cause the wave to be opposite. Let's see this in practice, maybe before I do the rest of the calculation. So here's an example. You see what happens at the very end? The pulse comes in, and then it is inverted at the end. Everybody see that? All right, let me do it again. So watch it again. It's inverted at the end when it's reflected. That's why we have that minus sign in there. Okay, now let's look at the math a little bit. All right, so we're adding these two waves together. All right, so just like before, we get 2a sine kx sine omega t. We get a sine here instead of a cosine because of this minus sign here. All right, but it's the same math as before. All right, now we have what are called boundary conditions. All right, we're going to assume that at both ends the rope is fixed, even though where it's vibrating it actually has a little amplitude, and that's going to be a source of kind of error for us. Okay, so we're not going to be able to get perfect standing waves with this simulation, but we'll get pretty close. All right, so we're going to assume that at one end and the other end it's fixed. All right, so what that if we set one end to be x equals 0, that's automatically done by this, because the sign of 0 is 0, no matter what k is. And it's 0 for all time. What about the other end at x equals, what did I call it, L? So we want y at L of t to equal 0. So this has got to equal 0 for all values of t, all values, at x equals L. Well, the only way that happens is if KL is an integer multiple of pi. All right? So we call that value of k, k sub n, and we have k sub n L has to equal n pi. All right? And that is the condition for what are called standing waves. So we have only at certain wavelengths will this work. Will be exactly like that. And it'll match the boundary conditions. And I'll show you what happens if you don't do this. All right, you'll see in the simulation. So that means k equals kn equals n pi. So lambda n equals 2 pi over kn. All right, kn is n pi over L. The pi's cancel, and you get 2L over n. So this is the condition for a standing wave. You have to have a wavelength that is 2 times the length of the wave, of the string, divided by an integer. All right? And if you do the frequency equals v over lambda n, you get that. Okay? So this is how on a violin, or a cello, or a viola, or a bass, or a piano, or a guitar, this is how you get different frequencies. Because the standing waves have a higher amplitude than other things. The other waves will kind of cancel out, because there'll be so many different ways in which they move. But only the standing waves have a higher amplitude. In addition, another key point here, notice every point on a standing wave has the same exact time dependence. So every point is moving with the same frequency, up and down, exactly the same. So let's see what that means physically. So I'm going to try and show you that on this simulation. So we're going to oscillate this. All right, so here is a wave. It's not a standing wave. All right? If it was a standing wave, you wouldn't see the maximum kind of moving back and forth like it is now. All right? So I have to try and figure out where the standing wave is. I have to change the frequency to get a standing wave. Let's see if I could do that. All right, so I'm going to try making this a little better. I'm going to knock down the amplitude a little bit. So that's better, but not perfect. Part of the problem is this thing is not fixed at the end. So the condition we had over here is not true. But if you look at it a little bit, it more or less, let's see, is, it's not traveling as much down the wave. It's mostly going up and down. And that would be a standing wave. Let me try and make the amplitude smaller. I'm going to cut the damping down to nothing, and then make the amplitude a little smaller. See if you, all right, so at certain times, see, there it didn't work, but see, it kind of goes into a standing pattern, and then it doesn't. And then there's a stand, see how that went up and down. So if I could do this perfectly, fix the frequency, I could get, I think that's about the best you could do. All right? So at certain times, you get a standing wave, very nice right now, and then it kind of poops out. And that's because this is not fixed over here. If it was fixed, I could get a perfect standing wave. But I can't do that. All right, let's see if I can make the amplitude a little smaller. Right now, it's like a standing wave, right there, see that? And then it kind of poops out, and that's because of this. That's about as close as I think I can get to a standing wave. All right. Now, let's, if you look down here, you see that the frequencies, NV over 2L, and lambda n is 2L over n. Okay. What would you say the wavelength of this is? Let's see if I can stop it in mid-frame. All right. So roughly, this is the wavelength right here. Okay, and then it goes through another there. All right, so that's the wavelength right there. So it's around 4.2. Everybody agree? Or 4.4? Right there is 4.4. Okay. What's L is about 7.5, something like that. So we have 2L is 15. So what would n have to be for this wave? What's the closest n it could be? Is it 1, 2, 3, 4, 5? What is it? The wavelength is roughly, roughly 5. So what is n? So what is it? 3. All right, so n is 3. That's roughly right. You get 1.5 wavelengths here. All right. So let's say I want to get the n equals 2 standing wave. All right, so I want the n equals 2 standing wave. The frequency right now is 1.5 hertz. What frequency should I set it to get n equals 2? Is the frequency lower or higher? Let's get that out of the way. Is it lower or higher for n equals 2 compared to n equals 3? What? Lower. All right, so what should it be? 1 hertz. That's a good guess. Because this is n equals 3 times something that doesn't change. And we got 1.5. So if we made it n equals 2, then it would be 2 times this. So 2 times 0.5 would be 1. All right, so let's see what happens. So I'm going to move the frequency down to 1. All right, so that's about the best we could do. All right, so it kind of works. Make the I wish I could make the amplitude smaller. So it didn't quite work. Let's see. So right here, go up there. Huh. That seems about the same. Same frequency. That should not be. What did I do? So I must, let's go back to 1.5. Let me make sure I got that right. Oh, slow motion. Yeah, that's good. Let's go slow motion. So that's 1.5 wavelengths. Oh, I see what, yeah. All right, so you have about 1. Let's see, when it actually goes, let's get the, so I'm going to get it when it's pretty, all right. So right there, so that was what we had before. It's right around there. About 5. All right, so about 1, 1.5. All right, now we go to 1. The frequency is 1. So n is 2, so the wavelength should be about 7 or so. Let's see, it should be longer. Yeah, it's not quite there yet. All right, let me go down. I'm going to go even further to half. Trying to get, maybe I'm going to work on getting the fundamental down right. It's pretty hard to get this to work, right? Maybe I need bigger amplitudes. It's close. Whoa. See that? So that's about the fundamental. So it's pretty much a half, which is what we said before. All right, so that's what you can see. See how it goes all the way up, then it comes all the way down. Now, if this was perfect, if I could get this amplitude down so that it really was oscillating without a big amplitude, I could do this better. Let's see if we can get it down. There you go, all the way down. So what you have is the fundamental with some extra thing thrown on top. And that's what makes it hard to see. So that would be the fundamental frequency. And then if we went to 1, we should get the next one. So you kind of see that, not very well. I think you actually see it better when you go to higher frequencies. Let's go to, let's say, 2. See if I can get it. So that's about, not quite, but that's what it would be. So that's what you would like is that it just goes up and down. All right? But the problem is this is not fixed at this end. And there's no way I can fix it and still oscillate the string. So you have a hard time doing that. In a real violin, both ends are fixed, right? And you excite it by just exciting it, okay? And in this, maybe I can try and do it manually. Let's try that. So I'm trying to get a standing wave there. There we go. See that? So I can sort of get a standing wave right there. There we go, not too bad. That's pretty good, actually. So I got it going, and then it keeps going. So there's a standing wave right there. All right, let's see if I can get it down to a fundamental. So here is like a fundamental. All right, so there's the standing wave fundamental. All right, everybody see it? So the reason why this is better doing it manually is because this is fixed. All I got to do is excite it, get it going, and then it's okay. All right, so that's the first one. Now let's see if I can get this second one. So it's not quite right, because it's moving, right? So it's moving back and forth. So it takes some skill to do this. I was able to do the fundamental pretty well, but getting the next one is not so easy. Let me try one more time. All right. I know it's a little faster than that. All right, that's not too bad. All right, so there's the n equals 2 almost. All right. I had n equals 1. That's pretty close to n equals 2, not perfect. Pretty close. And then if let's just try one more. All right, that's not too bad. Can almost do it. There you go. It's close, but almost the n equals 3 case. Okay? All right. So this is how all musical instruments work. They use this. Now, what about in wind instruments? Like a clarinet, or a tuba, or a trombone, or a trumpet. How do they work? Well, there you're using air. In some cases, you have a closed end, but in most cases, you have an open end at the end so that the sound can come out. All right, so what that is related to is this situation. You have no end there. And you have waves coming out at the end. And if I oscillate it, so you can have standing waves here also, where the wave just goes a certain amount and then it goes out. All right? So if you get the right frequency, you can get a standing wave here also. I probably can't do it very well, but you can get a standing wave here. So the difference turns out to be, let's see if I wrote it down. So the difference is that if you have an open wave, you don't have that reflection back and forth. So you don't have that minus sign in there. So in order to get a standing wave, you have a slightly different criteria. Lambda n is equal to, it has to be a half wavelength going through. And so you get the frequencies are 2n minus 1 times the fundamental instead of n times the fundamental. So you get odd frequencies of the fundamental frequency. So that's how like organs work. That's how various brass instruments and various woodwinds. Some of them have two open ends. Essentially, you're blowing into it, but you're also creating an open end because your mouth is not fixing the air when you blow in. But in others, you use a reed, which vibrates. And that vibration is forming the vibration. So for wind instruments, it depends on which way it's constructed as to whether you have two open ends, which are equivalent to two closed ends, or whether you have an open and a closed end. All right. So let me just end with a comment about the relevance of standing waves to other areas of physics. In particular, you know from chemistry, right, that atoms have particular states, right? They have discrete states that they're in. Everybody know that? You may have studied that in chemistry. So each atom, each molecule has a discrete state, okay? And that means it has a discrete energy. And it turns out that the light coming from that atom, when a state goes from one energy to another, the light is related to the change in energy, right? So the frequency of the light is related to the change in energy, all right? So in a sense, you could say each energy state, each state of the atom or molecule corresponds to a particular wave frequency. And they're discrete. Just like these are discrete here, the same thing is true in quantum mechanics, in quantum systems like molecules and atoms. And we call them, we usually don't use the word standing waves, we call them stationary states. And just like the standing waves here, they all have the property that they have the same time dependence for the state. So the state, every place in the system oscillates with the same standing wave pattern. So right now, everything that you're made of, the table, all molecules or atoms, everything, all these molecules are pretty much in stationary states. It's as if they're all standing waves. It's like you're just made up of a bunch of standing waves. That's what you really are. You're not really made up of particles. You're really made up of standing waves, all right? Stationary states. And that's what we are, all right? The idea of a particle is actually kind of problematic when one looks at quantum systems. Systems very tiny, all right? Instead, it's better to think of it as just being in a state. And the closest analogy to a state is a standing wave. That's the closest analogy to a state. All right. OK. So what do I want you to get out of this class? that everything we talk to, no matter how complicated it seems, no matter what the details are, it's all about adding waves together, superposition. All right? And then all you got to do is figure out what is constant and what changes in any situation. So for interference, path lengths differences are the key. In beats, having slightly different frequencies. In standing waves, you have two waves of the same frequency, same wavelength, going through each other and adding up. Okay.